This video
All right, so I got, what do I got? It's window capture. What? Browser capture? Browser capture. Gotta do work. I gotta do work. That is crazy. Come on, can I press the thing? That'd be great. That would be fucking outstanding. Do you not think? Great. Phenomenal. Phenomenale. Oh, my goodness, my goodness, my goodness. Ah, jeez. Oh, jeez. Okay, can we do this? There we go. Oh, wow. That's pretty fucking insane, actually. The hell? Sick. Wait, maybe I push myself here. That's maybe for the best. All right, buddy. There we go. So chapters. What chapters again? There we go. So chapters 26, 25. Is it 25, 26, 16, and 17? 16. $17. Okay, well, shit, dude. Electromagnetic induction. Okay, we gotta read this, basically. Alright, hello, we are covering chapters 25, 26, 16, and 17 from the textbook, Glencoe Physics Principles and Problems. I'm having trouble conceptualizing electromagnetic induction. Thank you. Okay, so this is it? 25? Okay, what's in this? No. What? Okay. Alright, let's see. Let's do this. Let's conceptualize magnetic induction, shall we? So, electromagnetism. Electromagnetism? Actually, it's 25. Electromagnetic induction. There we go. So, electromagnetic induction. Wait, what was it here? Contents in brief. Electromagnetic induction, electromagnetism. Okay. God damn it, dude. Alright, what you'll learn. You will describe how changing magnetic fields... You will describe how changing magnetic fields... Changing magnetic fields what? You will describe how changing magnetic fields can generate electric potential differences. You will apply this phenomenon to the construction of generators and transformers. Okay? Why it's important. The relationship between magnetic fields and current... Okay, wait, what you learn? You'll describe how changing magnetic fields can generate electric potential differences. Okay. Changing magnetic fields generate electric potential differences. You will apply this phenomenon to the construction of generators and transformers. Why it's important. The relationship between magnetic fields and current makes possible the three cornerstones of electrical technology. Motors, generators, and transformers. Okay, let's read that again, shall we? The relationship, so why it's important, the relationship between magnetic fields and current, so currents and magnetic fields, okay, make possible the three cornerstones of electrical technology. Motors, generators, and transformers. Hydroelectric generators. Dams commonly are built on rivers to provide a source of power for nearby communities. Within the dam, the potential and kinetic energy of water is turned into electric energy. Okay. Think about this. How did the generators located inside the dam convert the kinetic and potential energy of the water into electric energy? Okay. So how does water movement turn kinetic energy into electrical energy? What happens in a changing magnetic field? Okay, how does a changing magnetic field affect a coil of wire passed through it? Place to I don't know what to do with this because I don't have a lab. Get out of here. So 25.1, electric current from changing magnetic fields. In chapter 24, you learn how Hans Christian Ørsted, you mean the dragon god from Mushoku Tensei, discovered that an electric current produces a magnetic field. Yeah. Michael Faraday thought that the reverse must also be true, that a magnetic field produces an electric current. In 1822, Michael Faraday wrote a goal in his notebook, convert magnetism into electricity. Faraday tried many combinations of magnetic fields and wires without success. Okay, so he tried many combinations of magnetic fields and wires. So he had magnetic fields and wires, and he tried to induce an electric current in the wires with the magnetic field. Okay. After nearly 10 years of unsuccessful experiments, Faraday found that he could induce electric current by moving a wire through a magnetic field. In the same year, Joseph Henry, an American high school teacher... Wait. So what was his finding? So moving a wire through a magnetic field, right? Okay. Induces a current. Amazing. Oh yeah, that's because the electrons, if they're moving relative to a magnetic field, they experience a force, and if they're moving perpendicular to it, so they experience a force. Anyways, in the same year, Joseph Henry, an American high school teacher, also showed that a changing magnetic field could produce electric current. Okay, Mr. High School Teacher. So a changing magnetic field could also produce an electric current. So not only can you move a wire in a magnetic field perpendicularly to get an induced current, but you could also just vary the magnetic field, and that would induce a current. Okay. Okay, so in the same year, Joseph Henry, an American high school teacher, also showed that a changing magnetic field could produce electric current. Henry took an idea developed by another scientist and broadened the application to other educational demonstration devices to make them more sensitive or powerful. Henry's versions of these devices were not new discoveries, but he made the devices more dramatic and effective as an educational aid. However, Henry, unlike Faraday, chose not to publish his discoveries. Okay, because he couldn't be bothered. He couldn't be bothered to like help humanity out, huh? So, objectives for this section: explain how a changing magnetic field produces an electric current. Okay, define electromotive force. Solve problems involving wires moving in magnetic fields. Vocabulary: electromagnetic induction. What? Oh, electromagnetic induction. Fourth right-hand rule. Electromotive force. Electric generator, average power. Okay. I need to drink some water if I want to be reading this. Is this just chatting, I wonder? Did I put this in just chatting? Oh yeah, education. It is education. That's crazy. Alright. Yeah. When a wire is moved in a magnetic field, what about it? Actually, let's probably do it like this, actually. Let's just do it like this. What was I saying? Yes. So, when a wire is moved in a magnetic field, there is an electric current in the wire. Okay? Okay, but only while the wire is moving. The direction of the current depends on the direction in which the wire is moving through the field. The arrows indicate the direction of conventional current. Okay, so if you move a wire... So what does that mean, though? If you move the wire upwards... What happens when you split a magnet in two? Well, you create two new magnets that both have a north and south pole. Yeah. Apparently most students now that I'm teaching are all like magnets and like electromagnets and stuff. So I'm like, okay, I gotta review this stuff a little bit. I'm just gonna read like in today's stream, I'm just gonna read like the chapter on this, and then I'm gonna play Ghost of Tsushima. But I gotta do this because I got fucking no time, it would seem. Like I'm just doing too many things. How are you, Barbuda? I hope you're well. Okay. I want to keep reading this though. While talking to you. So if you have a wire, right? If you have a wire and you like move it perpendicularly to a magnetic field, then the electrons start moving because they experience a force, and then I guess that's why current starts. You induce a current by moving shit. Okay. So the direction of the current depends on the direction in which the wire is moving through the field. The arrows indicate the direction of conventional current. Okay, so moving it up, you have conventional current going this way. If you move it down, you have a different direction. Okay, amazing. Opposite direction. Fantastic. We've learned so much. Electromagnetic induction. So figure 25.1 shows one of Faraday's experiments in which a wire loop that is part of a closed circuit is placed in a magnetic field. When the wire is held stationary or is moved parallel to the magnetic field, there is no current. Yes, because by the way, if you have charges, so the way it works is that if you have charges and they're in a magnetic field, if they move in a perpendicular direction, like if they have a component going in a perpendicular direction to like the magnetic field direction, then they experience a force for some reason. Like, who the fuck knows? But if you move them parallelly, they experience no force. So, stuff. So that's what they're talking about. So when the wire moves... When the wire is held stationary or is moved parallel to the magnetic field, there is no current. But when the wire moves up through the field, meaning perpendicularly, the current is in one direction. When the wire moves down through the field in the opposite direction, sure, the current is in the opposite direction. An electric current is generated in a wire. So an electric current is generated in a wire only when the wire cuts magnetic field lines, meaning moving perpendicularly. Yes. Faraday found that to generate current, either the conductor can move through a magnetic field, or a magnetic field can move past the conductor. So it's the relative motion between the wire. So it is the relative motion between the wire and the magnetic field that produces the current. So you can move one or the other. You can move the magnetic field, or you can move the conductor. Okay, but like, what does it mean to move the magnetic field? To move the source of the magnetic field? Because you can't move, I mean, pretty much, that's what that means. So you move the source of the magnetic field. Because I don't know how you move field lines otherwise. The process of generating a current through a circuit in this way is called electromagnetic induction. Okay? So moving a field or a wire relative to the other. Amazing. But perpendicular directions, though. Anyways, how can you tell the direction of the current? To find the force on the charges in the wire, use the fourth right-hand rule. Jesus Christ. The fourth right-hand rule? So the problem, dude, with teaching is that, like, the problem with teaching many different courses and many different students is that, like, everybody has their own fucking textbook and their own fucking ways of doing things, and they're all, like, the same, but really they have different terminologies. And you're like, why is it the fourth right-hand rule when, like, no other textbook that I've seen says this? Okay, but to be fair, I haven't seen too much of the other textbooks. But it doesn't matter. So, how can you tell the direction of the current? To find the force on the charges in the wire, use the fourth right-hand rule. Okay? So, to hold your right hand, so I already know this. Hold your right hand so that your thumb points in the direction in which the wire is moving. Yeah. Well, yeah, this is basically you point your thumb in the direction of the velocity of the charges, okay? And then you open your palm up in the direction of the magnetic field, and then the direction of your palm will give you the conventional current. But the problem is, wait, hold your right hand. I remember the right-hand rule from school. Yeah, dude, the fucking right-hand rule. There's apparently, like, many of them, like, right? There's a few. I don't have limbs right now to show you, because I don't have that easy leap motion technology on me, which I probably should buy, to be quite frank. But there are a few of these. Anyways, so how can you tell the direction of the current? To find the force on the charges in the wire, use the fourth right-hand rule to hold your right hand so that your thumb points in the direction in which the wire is moving. So that's the charge direction, charge velocity direction, and then your fingers point in the direction of the magnetic field. So there's a few of these, by the way. You can either use all your fingers, or you can just use your forefinger and then curl in 90 degrees your third finger, right? Your middle finger, and then that'd be basically the same thing. I don't like these. This is called the slap roll. I don't know, it's weird. The palm of your hand will point in the direction of the conventional positive current as illustrated in figure 25.2. So if the motion of the wire is this way, and so this way, and then your fingerinos are in the direction from north to south, you go here, and then your force is obviously direction of your palm, or the direction of your middle finger if you kind of like close it a little bit. But on the diagram of the hand, you can lift the middle finger up to represent the... Yeah, exactly. That's what we're both talking about, the same thing. Yeah. I prefer the one where you lift your finger up like 90 degrees because you know it's a right-angled system. Damn it. A right-hand system. Yes, because that's just like kind of easier. That's how... So they taught me something else in school, by the way. Like I know this one, like we saw it in school, but there was another one, which was basically if you want to find the cross product between any two vectors, let's say the cross product between V and B, then what you're doing is you're putting your palm, like all of your fingers, right, like in the direction of the first vector, and then you curl your fingers in the direction of the second vector of your cross product. This was like a math thing though. Which like almost never shows up like in the physics things that I read. It's like they do all these different types of things. Why don't you just teach people what a cross product is, and you fucking just like use one method, you know? Like why don't you just do that? Like wouldn't that be simpler? Or am I crazy because I don't know enough? Is that why? Or like all but the pointed fingers? Yeah. Yeah. Anyways. You know, like the cross product method in math, right? Anyways, electromotive force. So this is what's happening, right? So like, oh, in the direction of the motion of the wire. Actually, yeah, the motion of the wire. And then because it's stationary inside. Yeah, and then you sorry, just because I have to like just look at this one more time because I need to legitimately have these images in my head when I teach. This is easy though, obviously. It's just that I'm trying to multitask here. Anyways, electromotive force. When you studied electric circuits, you learned that a source of electrical energy, such as a battery, is needed to produce a continuous current. Yes. The potential difference, or voltage, given to the charges by a battery. By the way, your voltage is really just your, right? Like your charges. There's work done from the battery on the charges to take the negative charges and then put them at the more negative place to create like a dipole system thing. So you transfer chemical energy into the charges. What's the into electric potential energy? Yes. So from chemical energy to electric potential energy, and then those charges move throughout the circuit, and then as they pass through resistances, they dissipate energy through heat, sound, light. Maybe not sound, like heat and light. Okay, maybe just heat and light. Maybe a little sound, maybe just a little bit. I don't know actually, but it should be all three. Anyways, actually, you know, quite a lot though, I'll be honest. So when you study electric circuits, you learn that the source of electrical energy, such as a battery, is needed to produce a continuous current. The potential difference, or the voltage given to the charges by a battery, is called the electromotive force, or EMF. So the potential difference or voltage given to the charges is called the electromotive force. Okay, so the electromotive force is a potential difference. Is that what that means? Or is it not the force? I guess it has units of force, probably. Or EMF. Electromotive force, however, is not actually a force. Oh my god! Spoilers! I knew it. I fucking knew it. Electromotive force, however, is not actually a force. So the electromotive force is a potential difference, and it's measured in volts. Okay. Why you call it a force? Because it starts the charge movement? Is that what is happening? Anyways, electromotive force, however, is not actually a force. Instead, it is a potential difference and is measured in volts. Thus, the term electromotive force is misleading. You're telling me. Like many other historical terms still in use, it originated before the related principles. In this case, those of electricity were well understood. The EMF is the influence that makes current flow from lower to higher potential. The EMF is the influence that makes current flow from lower to higher potential. Okay, but does that mean that in your idea of current, you're talking about like electrons, not like positive current, not conventional current? The gravitational force is actually not, is also not actually a force. Wait, what do you mean the gravitational force is also? I mean, it is a force. What are you talking about? It comes from a gravitational field. Well, I mean, are you talking about like the gravitational force is an interaction between particles, like the graviton? Is that what you're talking about? What are you talking about? Are you talking about quantum mechanics and stuff? That's too far ahead for the high school students. At least, it's not, but it's like they reach it at the end, if anything. Anyways, so this is something that, so I'm gonna like open up ChatGPT because ChatGPT is like pretty cool. If you know enough, right, you can use ChatGPT, and when it lies to you, you'll be like, that doesn't sound right, and then you use like something else. But I really want to figure out something. So here it says, where is it? The EMF is the influence that makes current flow from lower to higher potential, like a water pump and a water fountain. Yeah, I get that. But my question is, Particularly, it makes current flow from lower to higher potential. So I have to review, what does lower and higher potential mean? So explain this to me, Mr. GPT. The EMF is the influence that makes current flow from lower to higher potential like a water pump. Yeah, explain this to me. So what is it going to say? The sentence you quoted is trying to explain electromotive force using an analogy. Okay, so first, remember Ohm's law, potential difference, current, resistance. Normally, current flows from higher potential to lower potential through a circuit element like a resistor. Okay, yeah, that's my confusion here. So what the fuck are we talking about? Normally, current flows from higher potential to lower potential through a circuit element like a resistor. Okay? The problem, charges lose energy in the circuit. As current flows through resistors, but you know what? I'm just gonna, how do I show you this? How do I just do this? How do I just do, now I'm gonna need maybe another window for my ChatGPT. For my little ChatGPT. Or I could just share my screen. Can I do that? I can share my screen, but let me just hide all my real life info. Yeah, let's just do that. Fuck it. Display capture. Huh, huzzah. This is fine. Oh. Well, actually, I don't know if I want to show you this. Do I want to show you this? Maybe I'm going to hide my chats. Yeah, there we go. Sounds good. All right, let's see what this has to say. All right, so the problem, charges lose energy in the circuit. As current flows through resistors, bulbs, etc., charges lose electric potential energy. That energy becomes heat, light, etc. So by the time the charges return to the battery, they are at lower potential. If nothing pushed them again, the current would stop. Oh. It is due to the curving of spacetime according to Einstein and not just a straight-up attraction force that applies between objects according to... Yay, but like... Yay, like gravity bends, you know, space and time, I guess. That sort of thing. Like it bends the curvature of space, and that basically that's why objects go down, because they're going in a hole in space. But that's still a field that generates a force, that leads to a force. I don't know. We'd have to like talk definitions. What the fuck do you define as a force, really? Because so far nothing prevents what you said does not prevent the term force to be used for gravity. Basically, it just depends on why are you saying it's not a force. Like, what is a force, right? In general, and why would it not apply that definition to that? Anyways. Because what you could say, right, is that, like, because maybe you're just talking about gravitational field. Because gravitational force comes from the gravitational field. What is the bending of space-time called? No, it's fine. You're good, dude. You're good. If you want to talk about stuff, perfectly fine with me. I'm just going to take longer to do this, which means longer to get to Ghost of Tsushima, which is fine with me. It's just a question of if it's fine for you. If you're interested in this stuff. Also, what the fuck just happened? What? 1 sec. I gotta fish this back out now. So what does this say? So this is what my question was. So as the problem, charges lose energy in the circuit. So as current flows through resistors, bulbs, etc., charges lose electric potential energy. That energy becomes heat, light, etc. So by the time the charges return to the battery, they are at lower potential. If nothing pushed them again, the current would stop. Okay, so that's basically trying to solve the question of, like, after it passes through all the resistors, right? Why does it keep moving? What EMF actually does. EMF is the mechanism inside the battery or generator that pushes charges back up in potential. Oh, yeah. EMF is the mechanism inside the battery or the generator that pushes charges back up in potential. Okay, it's the mechanism. Okay, electromotive force is the mechanism. Batteries have EMFs. Inside the battery, charges go from... Okay, so this is what happens inside the battery, not in the wire. Okay. Inside the battery, charges go from low electric potential to high electric... Oh, okay, I understand. I'm just fucking stupid. This is just talking about the battery. Just talking about, like, the process of how the battery fucking moves the charges up potential, which is what it's designed to do. So that explains it. I'm sorry, I didn't get all the sleep in the world. So EMF, yeah, inside the battery, EMF. Charges go from low electric potential to high electric potential. This is the opposite of what happens in the external circuit. Yes. The battery adds energy to the charges. Yes. Why the water pump analogy is used? Think of a fountain. Water flow analogy, the water system. Water flowing downhill, gravity losing energy, pump pushing water back up. In the electric circuit, current is through the resistors, charges losing electric potential, therefore the battery EMF is raising the potential. It's the pump. Yes. The battery EMF is the pump of electrical energy. Of electric potential. Amazing. So water naturally flows downhill. A pump pushes it back uphill. Similarly, charges naturally move from high to low potential. The EMF of the battery pushes them from low to high potential. Sure. What EMF actually means physically. EMF is energy supplied per unit charge. EMF is energy supplied per unit charge. Units of volts, which is joules per coulomb. So a 9-volt battery means that every coulomb of charge gains 9 joules of energy inside the battery, okay? So units are volts, okay? So volts is really just energy per coulomb, okay? In one sentence, EMF is the energy source, like a pump, that pushes charges... EMF is the energy source, like a pump, that pushes charges from lower potential back to higher potential, allowing current to keep flowing around the circuit. If you'd like, I can also explain why it's called electromotive force, even though it's not actually a force, which confuses a lot of physics students. Yeah, go for it. Tell me why. Tell me why. Da-na-na. Great question, because the name electromotive force is honestly a bit misleading. Why it sounds like a force? The name suggests something like Newton's forces, F equals ma. A real force pushes on objects and has units of newtons, but EMF is not a force and it does not have units of newtons. Instead, EMF has units of volts, which are energy per charge. What EMF actually measures. EMF tells you how much energy a source gives to each unit of charge, so epsilon, the EMF, is equal to W over Q, which is the energy supplied over the charge. So a 12-volt battery means each 1 coulomb of charge gets 12 joules of energy. No forces are required in this definition. It is purely energy per charge. So EMF is energy per charge. Why the word force stayed? Historically, in the early 1800s, scientists did not yet have the modern concept of electric potential energy. They thought of electricity in terms of forces pushing charges, so which kind of makes sense, because that's kind of how I was thinking about it. They thought of because of the, charges, magnetic field, but doesn't matter. They thought of electricity in terms of forces pushing charges, so they named the quantity electromotive force, meaning roughly the thing that moves electricity. Later, we realized it is really a potential difference created by non-electrostatic processes, chemical reactions in batteries, magnetic induction in generators. Okay? But by then, the term EMF was already everywhere in physics and engineering, so it stuck. The deeper physics. In a normal conductor, the electric field pushes charges from high potential to low potential. Inside the battery, something different happens. Chemical forces push charges against the electric field. That is what maintains the potential difference across the circuit. So EMF is really the work done by non-electric forces per unit charge to move charges through the source. Okay? EMF is really the work done by non-electric forces. The work done by non-electric forces per unit charge to move charges through the source. Okay? Cool. Work done joules per unit charge coulombs to move charges through the source. A clean mental picture. Think of the circuit as an energy loop. Battery EMF gives energy to charges through potential difference pushing. Circuit elements, resistors, bulbs take that energy and convert it to heat and light. Charges return to the battery with lower energy. The battery recharges them again. Yep. Exactly like a water pump continuously lifting water in a fountain. Quick intuition to remember. Voltage difference in a circuit is energy lost by charges. EMF of a battery is energy given to charges. If you want, I can also explain the subtle but important difference between EMF and voltage, which confuses even university students. Sure. Go for it. Make me smart. Good. This is actually one of those things that separates surface understanding from real circuit intuition. People often say EMF equals to voltage, but that is not strictly true. Voltage is simply the difference in electric potential between 2 points. V is equal to W over Q. This means potential difference is equal to energy change over charge. So voltage tells you how much energy a charge loses or gains when moving between 2 points. Examples, across a resistor, energy turns into heat. Across a bulb, energy turns into light plus heat. Okay? Voltage is therefore something you can measure between any 2 points in the circuit. But EMF is a property of the source. battery. EMF is a property of the source. Battery, generator, solar cell. So it's not the same as potential difference because it's not the difference between 2 points. It's a property of the source. It tells you how much energy per charge the force supplies. So a 9, how much energy per charge or supplies. So a 9 is the property of the source, okay? So EMF is how much energy per charge is supplied to charges, while potential difference is the difference in electric potential between 2 points, which are very different things. Yeah, so this is a voltage potential difference is talking about the difference between 2 points, basically like a spatial difference. Like, hey, anything moving through here will experience this, while EMF is talking specifically about the amount of energy that is supplied by the source to the charge. So a 9-volt battery means that each coulomb of charge receives 9 joules of energy inside the battery, okay? The key difference, the easiest way to understand it, concept EMF, what it describes, energy given to charges by the source. So EMF is energy given to charges by the source. Voltage drop is the energy taken from charge by circuit components. Okay, but now you're saying voltage drop. You're not saying potential difference. Why are you doing this to me? Why won't you just tell me the fucking difference between potential difference and EMF? Why voltage drop? That's just like a negative potential difference. Why don't you fucking, what about a positive potential difference? What the fuck do I call that, huh? Huh? You motherfucker. Think of it like economics. EMF is your salary. Bro, economics, really? EMF is your salary. Voltage drops are your expenses. Amazing. Wow. Your money goes around the loop. Why they are often the same in textbooks. If you connect an ideal battery to nothing else, the voltage across its terminals equals the EMF. So students learn that voltage across the terminals is EMF. But this is only true when no current flows. Okay? Okay. So if it's not connected to anything, its voltage difference is equal to its EMF. Well, no fucking duh. But this is only true when no current flows. The important real-world case, internal resistance. Real batteries have internal resistance. When current flows, some energy is lost inside the battery itself. Okay, real batteries have internal resistance. When current flows, some energy is lost inside the battery itself. Then the terminal voltage becomes V equals to epsilon minus IR because of the internal voltage. Sorry, the internal resistance. Meaning that the battery produces more energy than you actually receive outside. Part of it is wasted internally as heat. Okay? Energy view of a full circuit loop. In one full loop, energy given by battery is epsilon. Energy lost in resistors is IR1 plus IR2 plus IR3 plus ... Energy lost inside the battery is IR. Energy lost inside the battery is IR. Sure. Yeah. Energy conservation gives epsilon is equal to I, R1 plus R2 plus ... plus R, which is basically Kirchhoff's loop rule. The clean intuition, think of charges like workers carrying energy backpacks, okay? Battery fills the backpack, resistors drain the backpack. By the time the charge returns to the battery, the backpack is empty again, the battery refills it. Ultra simple summary. Voltage is the energy difference between 2 points. EMF is the energy supplied by the source to keep current flowing. Okay, I don't need more of you. I think I've had enough of you, ChatGPT. I think I understand what this fucking means. You crazy bugger. Alright. How much more is left of this fucking section, dude? How much fucking more? How many sections are there, actually? Let's take a look. Let's make a count of how many sections there are. But there's quite a few sections. Oh, wow. There's 2 sections. There's only 2 sections? Bro, there's only 2 sections. It's crazy. Huh. That's nice. Yo, I gotta go get a snack real quick, okay? Like, we're not done with this, but snack time. Can I make this a different color? Perhaps. Is there a color? Select the color. Alright, let's do this. Alright, let's do this. Right back. I gotta fucking snack because I haven't eaten the shit today. Alright, I'm here. Alright. I'm back. Alright, let's do this. So I have like food to eat as well. It's very important to me. Somebody was burning something in the kitchen, so I had to step away for a moment. Someone was making cookies and they forgot about them. Unfortunately.
I'm taking it slow, but I just want more. I'm taking it slow, just go with the flow. I'm taking it slow, my knees on the floor. I'm begging for more. It's you I adore.
I got lost tonight under the stars up in the sky. Directions hard to find under the stars up in the sky. I got lost tonight under the stars up in the sky. Directions hard to find under the stars up in the sky. I don't know where to take this, I don't wanna break this. We're living in the moment, living in the moment. Your head is on my shoulder, we're never getting older. Baby, it's you and I, you and I. Yeah, we're stars in the sky. Oh, you and I. Yeah, we're stars in the sky. You say that you're leaving me, the same thing you said last night. You can't do it peacefully, you won't go without a fight.
All right.
So when I go, I know you'll follow me. I don't want slamming doors, no, no. Just wait and see, you'll feel it naturally. There's no one else I see, I know you'll follow me. I don't know where to take this, I don't wanna break this. We're living in the moment, living in the moment. Your head is on my shoulder, we're never getting older. Baby, it's you and I, you
Oh my god, that was a good snack. Oh, that was a good snack. That was nice. When you move a wire through a magnetic field, okay, you exert a force on the charges and you move in the direction of the force. Work is done on the charges. Okay. Oh. Oh. You move the wire this way. It pushes, there's a force, which means there's a current. Huh. Interesting. Okay, so when you move a wire through a magnetic field, you exert a force on the charges and they move in the direction of the force. Work is done on the charges. Their electric potential energy, and thus their potential, is increased. The difference in potential is called the induced EMF. Interesting. Induced EMF. All right, I've eaten enough. Wait, what? What are the units of this? Wait, what? What's my other thing? Whoops. Where is it? Forces in magnetic field. I think it was this one. I don't want to watch your video.
This
I just
video is
I don't want to watch your
for
video. I don't want to watch your video. I just want the formula that I'm looking for. Just want the formula that I'm looking for. Where's the formula that I'm looking for? This is it. Force is equal to BIL sine theta. Okay. And what is so this is BIL sine theta. Ah, this is BLV sine theta. Okay. That's nice. Okay, so there's a difference here between this and between this. That's nice. Anyways, so electromotive force, EMF equals to BLV sine theta. Electromotive force is equal to the magnitude of the magnetic field times the length of the wire times the component of the velocity of the wire in the field perpendicular to the field. Nice. If a wire moves through a magnetic field at an angle to the field, only the component of the wire's velocity that is perpendicular to the direction of the magnetic field generates EMF. If the wire moves through the field with a velocity that is exactly perpendicular to the field, then the above equation reduces to EMF equals to BLV, because sine of 90 equals to 1. Checking the units of the EMF equation will help you work algebra correctly in related problems. The unit for measuring EMF is the volt. V, in chapter 24, B was defined as F equals to I over L. Therefore, the units for B are N over AM. Okay. Sorry, N over A. Sorry, newtons per amp meters. Whoops. Velocity is measured in meters per second using dimensional analysis. Recall from previous chapters that joules equals to Newton meters. A equals to C over seconds. Therefore, G joules per coulombs is V equals to joules per coulomb. Okay. In this drawing of a moving coil microphone, the aluminum diaphragm is connected to a coil. In this drawing of a moving coil microphone, the aluminum diaphragm is connected to a coil in a magnetic field. When sound waves vibrate the diaphragm, the coil moves in the magnetic field and generates a current that is proportional to the sound wave. Wow. A microphone is a simple application that depends on an induced EMF. A dynamic microphone is similar in construction to a loudspeaker. The microphone shown in Figure 25.3 has a diaphragm attached to a coil of wire that is free to move in a magnetic field. Sound waves vibrate the diaphragm, which moves the coil in the magnetic field. The motion of the coil, in turn, induces an EMF across the ends of the coil. The induced EMF varies as the frequency of the sound varies. In this way, the sound wave is converted to an electrical signal. The voltage generated is small, typically 10 to the negative 3 volts, but it can be increased or amplified by electronic devices. Okay. So what did we learn? If a wire moves through a magnetic field at an angle to the field, only the component... Yeah, we know this. So when you move the induced EMF, it depends on the magnetic field. The wire and the induced... Okay, velocity of the wire is... Okay, cool. Okay. Electric generators. The electric generator invented by Michael Faraday converts... Wait, how many pointers do I have left? 1, 2, 3, 4. Okay, we have a little bit. We have a little bit left. Okay, we're almost done. Electric generators. The electric generator invented by Michael Faraday converts mechanical energy to electrical energy. An electric generator consists of a number of wire loops placed in a strong magnetic field. The wire is wound around an iron core to increase the strength of the magnetic field. So in other words, okay, the iron and wires are called the armature, which is similar to that of an electric motor. The armature is mounted so that it can rotate freely in the magnetic field. As the armature turns, the wire loops cut through the magnetic field lines and induce an EMF, commonly called the voltage. The EMF developed by the generator depends on the length of wire rotating in the field. Increasing the... The armature is mounted so that it can rotate freely in the magnetic field. As the armature turns, the wire loops cut through the magnetic field lines. As the armature turns, the wire loops cut through the magnetic field lines. Okay. As the armature turns, okay, The wire loops cut through the magnetic field lines and induce an EMF, commonly called the voltage. The EMF developed by the generator depends on the length of wire. So I have a question for ChatGPT. So, where's my ChatGPT? So, help me understand generators and induced EMF microphones. Step by step. So generators and microphones both come from the same core physics, electromagnetic induction. Once you understand the principle, both devices become almost obvious. And the core idea, changing magnetic flux actually means... Wait. The core idea, changing magnetic flux creates EMF. Everything starts with Faraday's law. Well, can you explain it? Can you explain it at a high school level without calculus? Everything you need to know comes from one simple rule. If a wire experiences a changing magnetic field, a voltage is created in the wire. Okay? This is called electromagnetic induction. The key idea is simple version. If you have a magnet, a loop of wire, and something moves, electricity can appear. 3 ways to make that happen. Move the magnet, move the wire, rotate the wire. Any motion that changes how the wire sits in the magnetic field can produce EMF. Any motion that changes how the wire sits in the magnetic field can produce EMF. Okay. Generator, mechanical energy, electricity. A generator is basically a coil of wire spinning inside a magnetic field. You place a loop of wire between 2 magnets. Magnetic field lines go through the loop. You rotate the loop using mechanical energy. This would come from wind turbines following water, hydroelectric dams, steam turbines in power plants. Step 3, as the loop rotates, the wire cuts through magnetic field lines. When that happens, electrons in the wire get pushed. Electrons start moving. Moving electrons equals an electric current, so the generator converts motion into electricity. Okay? Why the electricity alternates? AC. As the loop keeps rotating, half the turn pushes electrons one way. Oh, why the electricity alternates? Oh, AC current. As the loop keeps rotating, half the turn pushes electrons one way, the other half pushes electrons the opposite way. So the current goes forward, backward, forward, backward. This is alternating current. Microphone sound to electricity. A dynamic microphone works with the same physics. Instead of spinning a coil, sound moves it. Okay. Step by step. Sound arrives. Sound is just vibrating air pressure. When you speak, the air moves in waves. Diaphragm vibrates inside the microphone is a thin sheet called a diaphragm. Diaphragm. Sound waves push it back and forth. Coil moves in a magnetic field. Attached to the diaphragm is a tiny coil of water. There's also a magnet nearby. When the diaphragm moves, the coil moves inside the magnetic field. Voltage appears. Because the coil is moving in the magnetic field, a tiny voltage is produced. That voltage follows the same pattern as the sound wave, so the microphone converts sound vibrations to electrical signal. Oh, nay. Why the signal matches the sound. If you speak louder, diaphragm moves more. Coil moves more. Bigger voltage. If you speak softly, smaller movement, smaller voltage. High pitch, faster vibration. Low pitch, slower vibration. So the electrical signal becomes a perfect copy of the sound wave. The beautiful symmetry. These devices are almost mirror images. Generators spin coils, which turn mechanical energy into electrical energy. Microphones vibrate coils, which turn sound energy into electrical energy. Okay. Speakers, coil pushed by current, generates sound, electrical sound. Okay, a speaker is basically a microphone run backwards. The one sentence that explains everything. Moving a wire in a magnetic field pushes electrons in the wire. That single idea explains generators, microphones, electric guitars, induction cooktops, transformers, wireless charging. Almost half of modern electrical technology comes from this principle. If you'd like, I can also show you the extremely nobody cares. Okay, so what you're saying then is so a microphone is a simple application that depends on an induced EMF. A dynamic microphone is similar in construction to a loudspeaker. The microphone shown here has a diaphragm attached to a coil of wire that is free to move in the magnetic field. Sound waves vibrate the diaphragm, which moves the coil in the magnetic field. The motion of the coil, in turn, induces an EMF across the ends of the coil. Okay. What was the EMF again? Induced EMF. across the ends of the coil. So help me explain induced EMF. How do I visualize induced EMF? I'm having a hard time seeing the coil and what the EMF looks like inside the coil. The problem is that textbooks jump straight to formulas, but induced EMF is really about motion and forces on electrons. Let's build a visual picture you can hold in your head. First, imagine a straight wire moving through a magnetic field. Forget coils for a moment. Picture a straight metal rod moving sideways through a magnetic field. Inside the wire are free electrons. When the wire moves through the magnetic field, the electrons feel a magnetic force. That force pushes them towards one end of the rod. Result, one side becomes negative, the other becomes positive. That separation of charges creates a voltage across the rod. That voltage is induced EMF. So this, okay. So the simple picture is moving wire, electrons pushed, voltage appears. Now connect the rod in a loop. Now instead of a single rod, imagine it is a part of a closed loop of wire. Now when the electrons get pushed, they cannot just pile up, they start circulating around the loop. That moving charge is current. So when you have a rod, okay, the moving charge is current. So now we have motion, charge pushed, current flows in loop. Why coils are used instead of one loop? A generator or microphone uses many loops of coil. Why? Because each loop experiences the push from the magnetic field. The voltages from each loop add together. Example idea, one loop, small voltage, 100 loops, 100x, the larger voltage. So the coil is just many loops stacked together to amplify the effect. How to visualize the EMF inside the coil. Here's the mental picture that helps most students. Think of the coil as a circular racetrack for electrons. When the coil moves or rotates in a magnetic field, the magnetic field pushes the electrons along the track, like wind pushing runners around the track. Okay? The EMF is basically the push around the loop. Okay, so EMF is not a point, it is a driving push along the entire loop. What happens in a rotating generator? Now picture the coil rotating between magnets. When the coil turns, picture the coil rotating between magnets. When the coil turns, sometimes the wire moves across the magnetic field strongly, sometimes they move parallel to the field. Okay. Sometimes what happens in a rotating generator? When the coil turns, sometimes the wire moves across the magnetic field strongly, sometimes they move parallel to the field. So the push on changes. So the push on electrons changes as the coil rotates. Strong push, large EMF. Weak push, small EMF. Opposite direction, EMF reverses. This is why the voltage from generators oscillates like a sine wave. Another helpful visualization, cutting magnetic field lines. Many teachers describe it like this. Magnetic field lines pass through space. When a wire moves through them, it cuts through the lines. Each time it cuts through field lines, electrons get pushed. More cutting, more EMF. Faster motion, more cutting, bigger EMF. The deepest way to visualize it, instead of thinking EMF appears in the coil, think the magnetic field pushes electrons around the loop. EMF is simply the total push around the entire circuit. It is like a circular pressure that drives charges, the three-step mental model. Whenever you see induction, imagine this movie. Wire moves in a magnetic field. Magnetic field pushes electrons sideways. Electrons circulate around the loop. That circulation is induced current. Okay. One sentence intuition. Induced EMF is the magnetic field pushing electrons around the loop when the wire moves through the field or when the magnetic field through the loop changes. Induced EMF is the magnetic field pushing electrons around the loop when the wire moves through the field or when the magnetic field through the loop changes. If you like, I can also show you the single diagram that makes it instantly obvious. Okay, do that. The sliding rod generator, the simplest way to see induced EMF. This setup is the cleanest mental model for induced EMF. If you understand this picture, you understand generators and microphones. Okay, so imagine 3 pieces of metal, 2 metal rails, 1 sliding metal rod connecting them. Okay, together they form a closed loop. Now place the whole thing inside a uniform magnetic field pointing into the page. Wow. Okay. That's wild. That's wild. That AI can do this. Did it take them from somewhere? Where'd you take this from? Oh, okay, you've taken them from somewhere. You haven't generated them. It's phenomenal. Okay. So we have a magnetic field B into the page, rod sliding to the right, electrons inside the rod. What happens when the rod moves? As the rod moves, it's moving perpendicular to the magnetic field, so it would experience a force going upwards. So the current would go counterclockwise. Okay, cool. Inside the electrons inside the rod are also moving. So when the rod slides to the right, the electrons inside the rod are also moving through the magnetic field. Moving charges in a magnetic field experience magnetic force. That force pushes electrons towards one end of the rod. So the rod becomes one end negative, the other end positive. This separation of so the rod becomes one end negative, the other end positive. The separation of charge creates a voltage across the rod. That voltage is the induced EMF. Why current starts flowing? Because the rod connects the rails, the charges now have a path to move. Wait, so are you telling me that induced EMF is basically just a battery? It's basically just an induced battery? What? I'm gonna have to ask it. Are you telling me that an induced EMF is essentially just a battery, is just an induced battery, and when you connect that induced battery to wires, other parallel parts to the rod system, then they just move in the same way that the battery would make them move? Let me be clear. Is the rod that is moving, can it be considered, I know the words are bad, can it be considered an induced battery of sorts? Well, maybe not sure, the words are wrong, but you know what I mean. Yes, that is actually an excellent way to think about it. Your intuition is very close to how physicists interpret it. Let's refine it slightly so it becomes exactly correct. Yes, the moving rod behaves like a temporary battery. When the rod moves through the magnetic field, electrons inside the rod get pushed to one side, one end becomes negative, the other end becomes positive. That creates a potential difference across the rod. That is exactly what a battery does. So in that moment, the rod is acting like a source of EMF. You can absolutely think of it as a tiny induced battery. Absolutely, great. You can absolutely think of it as a tiny induced battery. What makes it different from a real battery? A normal battery creates EMF using chemical reactions. So a normal battery creates EMF using chemical reactions. A moving rod creates EMF using magnetic forces on moving charges. But electrically, the circuit does not care. All the circuit sees is a voltage source between 2 points. What happens when you connect wires? Exactly as you suggested, once the rod creates that potential difference, charges start flowing through the rest of the circuit. Exactly the same way they would with a battery. So the loop behaves like this. Induced EMF in rod, current around circuit. The rod is simply the location where energy enters the electrical system. Oh, that makes a lot of sense. The rod is simply the location where energy enters the electrical system. Where the energy actually comes from. This is the subtle but very important part. This is like work done by magnetic force, essentially. The electrical energy is not coming from the magnetic field. Oh, well, yes. That's true. Okay, this is subtle but very important part. Okay, the electrical energy is not coming from the magnetic field. It comes from whatever is pushing the rod. For example, your hand pushing the rod, a turbine spinning a generator, vibrating air moving a microphone coil. So the energy conversion is mechanical energy to electrical energy. The rod is the converter. Why the rod resists motion? Once current starts flowing, something interesting happens. The current in the rod creates its own magnetic force. Wait, what? Once current starts flowing, something interesting happens. Oh no, not interesting things. The current in the rod creates its own magnetic force that pushes against the motion. So when you try to push the rod, it pushes back. This is why generators require mechanical effort. What? The current in the rod creates its own magnetic force that pushes against the motion. So when you try to push the rod, it pushes back. This is why generators require mechanical effort. It is also why energy is conserved. The clean conceptual picture. You can think of the rod as a battery that only exists while it is moving. If the rod stops moving, electrons stop being pushed, charge separation disappears, EMF disappears, current stops. So the rod is like a motion-powered battery. Okay? Your statement rewritten perfectly. Your idea can be stated like this. A conductor moving through a magnetic field behaves like an induced voltage source. When connected to a circuit, it drives current just like a battery would. That is exactly correct physics. Final intuition. Battery, chemical forces push charges. Moving rod, magnetic forces push charges. But electrically they behave the same. Both create EMF that drives current around a circuit. Okay, so question. Question. Can circuits, can currents induced in this way be anything but AC, or are they all usually AC currents? Great question. The short answer is induced currents are not necessarily AC. They can be either AC or DC depending on how the magnetic situation changes. Let's break it down clearly. What induction actually requires. Induction only requires a change in magnetic flux. Translated to high school language, if the magnetic field through a loop changes, a voltage appears. That change can happen in many different ways. The type of change determines whether the current is AC or DC. One-time motion, temporary DC. Imagine the sliding rod generator again. You push the rod to the right at constant speed. While it is moving, electrons are pushed in one direction. Current flows in one direction. That is DC current. But it only lasts while the rod is moving, so this is temporary DC. If you stop moving the rod, the EMF disappears. The current stops. Case 2, back and forth motion, AC. Now imagine the rod moving right, left, right, left. Now the electron push keeps reversing directions. That means the current reverses directions too. So you get AC current. This is what happens in microphones and speakers. Case 3, rotating coil generator, AC. This is the classic power plant generator. A coil spins in a magnetic field. During one rotation, half the turn pushes electrons away, the other half pushes them the opposite way. So the current naturally becomes alternating current. That is why power plants generate AC electricity. How generators can make DC. How generators can make DC. You can convert that AC into DC using a device called a commutator. A commutator flips the connections every half rotation so that the current in the external circuit always goes the same direction. Early generators use this to produce DC electricity. Examples of both types: induced AC, power plant, generators, microphones, guitar pickups, transformers, induced DC, sliding conductor, generators, homopolar generators, generators with commutators. The deep principle: induction does not care about AC or DC, it only cares about change. If the change keeps reversing, AC. If the change stays in one direction, DC. Clean intuition. Induction produces whatever current matches the motion causing the magnetic change. Induction produces whatever current matches the motion causing the magnetic change. Steady motion, one way DC, oscillating motion AC. Amazing. So let's just finish reading this other thing. So what happens when the rod moves? When the rod slides to the right, the electrons inside the rod are also moving through the magnetic field. Moving charges in a magnetic field experience a magnetic force. That force pushes electrons towards one end of the rod. So the rod becomes because the voltage, the separation creates a voltage across the rod. Why current starts flowing? Because the rod connects the rails, the charges now have a path to move, so electrons begin traveling around the loop, through the rod, down the rail, across the bottom, back up the other rail. The charges circulate continuously. That circulating motion is electric current. The key inside the rod is physically pushing electrons around the loop. So the energy flow is mechanical motion, electron motion, electrical energy. This is exactly how generators work. Why the EMF depends on speed. If the rod moves slowly, small push on electrons, fast, big push on electrons. The faster motion produces larger EMF. The relationship is E equals to BLV. Okay, how this connects to coils. A rotating coil in a generator is basically many rods doing this at once. Each side of the coil acts like a moving rod cutting through the magnetic field lines. As the coil spins, one side moves up, the other side moves down. Each side generates EMF. That voltage combines to produce alternating current. Okay. Why this model is powerful. The sliding rod explains almost everything about induction. It explains generators, microphones, electric guitar pickups, induction cooktops. All come from the same idea: moving conductors in magnetic fields push electrons. The visualization you should keep. Imagine the rod is a plow moving through a field of electrons. As it moves through the magnetic field, it sweeps electrons to one side, creating a pressure difference that drives current around the loop. The pressure, whatever, man. So, are the coils? So how are the coils moving in the magnetic field? They are rotating along their axis. How do I visualize this? Okay, so here's a turbine. Here's a coil. This coil is rotating like this. Okay. What is this? Oh, it's rotating like this. Okay. Crank. Path of motion. Coil rotated by mechanical means. Okay. That's interesting. Oh boy. Oh boy. Like a rotisserie chicken or a Ferris wheel. Jesus Christ. Exit goes through the center of the loop. Okay. Now place the loop between two magnets, North Pole on one side, South Pole. The other magnetic fields go straight across the gap between the magnets, so the loop sits inside the uniform magnetic field. How the coil moves. Okay. Okay. Okay, cool. I think we've had enough of ChatGPT. Alright, what's next? So a microphone is a simple application. Yeah. Electric generators. So the electric generator invented by Michael Faraday converts mechanical energy to electrical energy. An electrical generator consists of a number of wire loops placed in a strong magnetic field. The wire is wound around an iron core to increase the strength of the magnetic field. The iron and wires are called the armature. Is this a loop? The fuck is it? The armature, okay, so the wire is wound around an iron core to increase the strength of the magnetic field. The iron and wires are called the armature, which is similar to that of an electric motor. The armature is mounted so that it can rotate freely in the magnetic field. The armature is mounted so that it can rotate freely in the magnetic field, okay? As the armature turns, the wire loops cut through the magnetic field lines and induce an EMF, commonly called the voltage. The EMF developed by the generator depends on the length of wire rotating in the field, increasing the number of loops if the armature increases. The generator depends on the length of wire rotating in the field, increasing the number of loops in the armature increases the wire length. Thereby increasing the induced EMF. Note that you could have a length of wire with only part of it in the magnetic field. Only the portion within the magnetic field induces an EMF. When a generator is current from a generator. When a generator is connected in a closed circuit, the induced EMF produces an electric current. Figure 25.4 shows a single loop generator without an iron core. Shows a single loop generator without an iron core. Okay. The direction of the induced current can be found from the third right-hand rule. Okay. As the loop rotates, the strength and the direction of the current change. Okay. Top view. Okay. The cross-sectional view of a rotating wire loop shows the position of the loop when the maximum current is generated. When the loop is vertical, the current is 0. The current varies with time as the loop rotates. The variation of EMF with time can be shown in a similar graph. Top view. Okay, the current is greatest when the motion of the loop is perpendicular to the magnetic field. That is, when the loop is in the horizontal position, as shown in figure 25.5a. In this position, the component of the loop's velocity perpendicular to the magnetic field is greatest. As the loop rotates from the horizontal to the vertical position, it moves through the magnetic field lines at an ever-increasing angle. This cuts through fewer magnetic field lines per unit of time, and the current decreases. When the loop is in the vertical position, the wire segments move parallel to the field, and the current is 0. As the loop continues to turn, the segment that was moving up begins to move down and reverses the direction of the current in the loop. This change in direction takes place each time the loop turns through 180. The current changes smoothly from 0 to some maximum value and back to 0 during each half turn of the loop. Then it reverses direction. A graph of current versus time is shown in figure 25.5c. Does the entire loop contribute to the induced EMF? No. It's just the sides that are inside of the magnetic field. Does the entire loop contribute to the induced EMF? Look at figure 25.6, where all 4 sides of the loop are depicted in the magnetic field. Well, I mean, no, only the side ones. Where all 4 sides of the loop are depicted in the magnetic field. If the fourth right-hand rule is applied to segment AB, the direction of the induced current is toward the side of the wire. Is it? Wait, how does that work? So it's really the top and bottom, really? So if the fourth right-hand rule is applied to segment AB, the direction of the induced current is toward the side of the wire. The same applies to segment CD. Thus, no current is induced along the length of the wire in AB or CD. It's just these two. Okay. But in segment BC, the direction of the induced current is from B to C, and in segment AD, the current is from D to A. Because the conducting loop is rotating in a circular motion, the relative angle between the point on the loop and the magnetic field constantly changes. The electromotive force can be calculated by the... Okay, because the conducting loop is rotating in a circular motion, the relative angle between the point on the loop and the magnetic field constantly changes. The electromotive force can be calculated by the electromotive force equation given earlier, except that L is now the length of segment BC. The maximum voltage is induced when a conductor is moving perpendicular to the magnetic field and the state is 90. Generators such as those in the chapter opening image work in a similar fashion. Potential energy from water stored behind a dam is converted to kinetic energy, which spins the turbine. The turbines in turn turn coils of conductors in a magnetic field, thereby inducing an EMF. Generators and motors are almost identical in construction, but they convert energy in opposite directions. A generator converts mechanical energy to electrical energy, while a motor converts electrical energy to mechanical energy. Okay, that is very nice of you. We're almost done with this. We're almost done. So, an alternating current generator transmits current to an external circuit by way of a brush slip ring arrangement. What the hell is this? The alternating current produced varies with time. The resulting power is always positive and always sinusoidal. Interesting. I don't know what the fuck this is. Brushes. Okay. Is this it? Okay, we just have to read this part, okay, and we're done. We read this last thing, and then we're done. So, alternating current generators. An energy source turns the armature of a generator. An energy source... So, alternating current generators. Oh, they're here. Okay. So, An energy source turns the armature of a generator in a magnetic field at a fixed number of revolutions per second. In the United States, electric utilities use a 60 Hz frequency in which the current goes from one direction to the other and back to the first 60 times per second. Figure 25.7a shows how an alternating current AC in an armature is transmitted to the rest of the circuit. The burst slip ring arrangement permits the armature to turn freely while still allowing the current to pass into the external circuit. Slip rings. Not sure why. Oh. Oh, brush. I see. Slip rings. I see. So this rotates. Wire. Okay, current is now in this. Wait, what? Brush. Okay. How does that work? Okay. Okay. That's interesting. Okay. I get it. I understand. Hmm. Wait, what? Oh. Okay. That is interesting. That is interesting. Determine I effective in terms of maximum current. Start with the power relationship PAC and substitute I r squared. Okay, so I squared r effective is equal to 1/2. Wait, what? How does that make sense? How does that make sense? How the fuck does that make sense? So it's common to describe alternating current and voltage in terms of effective current and voltage rather than referring to their maximum values. Recall from chapter 22 that P equals to I squared R. Thus, you can express effective current IF in terms of the average AC power as PAC equals to I effective squared times R. Okay? Yeah. To determine I effective in terms of the maximum current, I max, you know that that is equal to 1/2 I max. Oh, I see. 1/2. I see. 1/2 I max squared R. So then those things cancel out, and then you square both sides. Square root of 2 over 2. Effective current is equal to square root of 2 over 2 times the maximum current. Okay. Similarly, the following equation can be used to express effective voltage. Effective voltage equals to square root of 2 over 2 V max. Oh, okay. Effective voltage is equal to, okay, square root, 1 over square root of 2 times the maximum voltage. Okay. Effective voltage also is commonly referred to as RMS, root mean square. Effective voltage also is commonly referred to as RMS, root mean squared voltage. In the United States, the voltage generally available at wall outlets is described as 120 volts, where 120 volts is the magnitude of the effective voltage, not the maximum voltage. The frequency and effective voltage that are used vary in different countries. Okay, cool. In this section, you have explored how moving wires in magnetic fields can induce current. However, as Faraday discovered, changing magnetic fields around the conductor. So in this section, you have explored how moving wires in magnetic fields can induce current. However, as Faraday discovered, changing magnetic fields around the conductor also can induce current in the conductor. In the next section, you explore changing magnetic fields and the applications of induction. In the next section, you will explore changing magnetic fields and the applications of induction by changing what? And the next you explore changing in the applications of induction by changing magnetic fields. Okay. So section review. Generator. Could you make a generator by mounting permanent magnets on a rotating shaft and keeping the coil stationary? No. A bike generator? No. No. No, I don't really care about that. I think we're done for today. With this. So alright, I gotta read 6 more pages later. Alright, I'm done with this. It's fine with me. Alright, let's do this. Tsushima.